Entropy. This topic introduces entropy as a new thermodynamic property used to measure the direction and quality of a process. Entropy is not only related to the amount of energy, but also to the level of order or disorder of that energy. This concept is central to understanding the second law of thermodynamics in a quantitative way. In energy system analysis, entropy helps explain why not all energy can be converted into work. This chapter builds the understanding of entropy from a macroscopic and practical perspective. Lesson Plan Thermodynamics I. This section shows the position of the entropy topic within the overall structure of the Thermodynamics I course. Entropy is discussed after the second law because it is the mathematical formulation of that law. The chapter sequence shows the transition from energy analysis to energy quality analysis. Students are expected to already understand closed systems, control volumes, and the second law before studying this topic. Therefore, entropy becomes a bridge toward more realistic system performance analysis. Learning outcome. The learning outcomes emphasize the student's ability to use entropy in analyzing thermodynamic processes. Students are expected to relate the second law to entropy changes. In addition, students should be able to calculate entropy changes for various substances and processes. The concept of isentropic processes is also an important focus of this chapter. The final goal is the ability to use entropy as an engineering analysis tool. Clausius inequality development. This concept explains the interaction between a system and a thermal reservoir through a reversible cyclic device. By using a combined system, a general relationship between heat and entropy can be derived. The reversible cyclic device is used as a conceptual tool rather than a real system. This approach is important to distinguish between reversible and irreversible processes. From here, the Clausius inequality is developed. Volume change in cyclic process. In a cyclic process, the system returns to its initial state after one complete cycle. Although the volume may change during expansion and compression, the total volume change is zero. This confirms that all state properties return to their original values at the end of the cycle. This concept is important for deriving integral relations in thermodynamics. The cyclic nature forms the basis of Clausius analysis. Entropy change in processes. The entropy change between two states depends only on the initial and final states. Its value is the same for both reversible and irreversible processes. This shows that entropy is a property, not a path function. Although irreversible processes involve more energy dissipation, the entropy change remains the same. The difference lies in the amount of entropy generated. Check your understanding number 1. This section reinforces the idea that entropy is a state property. The main focus of the question is the dependence of entropy change on the initial and final states. It aims to strengthen the understanding of path independence. By understanding this, students will not confuse entropy with process paths. This concept is fundamental for all subsequent entropy analysis. Cycle with reversible and irreversible processes. This cycle combines one reversible process and one irreversible process. The initial and final state points remain the same even though the process paths are different. For analysis purposes, one process is assumed to be internally reversible. This approach simplifies the derivation of entropy relations. It also reinforces that entropy is a state function. Entropy in isolated systems. In an isolated system, there is no exchange of mass, heat, or work with the surroundings. The total entropy change of an isolated system is always greater than or equal to zero. This is a direct statement of the second law of thermodynamics. The total entropy change is the sum of the entropy changes of all subsystems. If the process is irreversible, the total entropy must increase. Isolated system characteristics. An isolated system includes both the system and the surroundings within a perfectly closed boundary. No energy and mass can cross this boundary. All internal interactions occur only inside this combined system. Therefore, the total energy and total mass remain constant. This concept is crucial for understanding the entropy increase principle. System and entropy change. The entropy of a system can decrease when the system rejects heat to the surroundings. However, this decrease is always compensated by an increase in the entropy of the surroundings. When the system and surroundings are combined, the total entropy never decreases. This concept introduces entropy generation as a measure of irreversibility. The value of entropy generation is always greater than or equal to 0. Answer B. The surroundings' entropy increase compensates for the system's entropy loss, and total entropy generation is never negative. Explanation. A. The system's entropy can decrease when heat flows in, but total entropy generation is negative. This is incorrect because the total entropy generation is always positive or 0, never negative. B. The surroundings' entropy increase compensates for the system's entropy loss, and total entropy generation is never negative. This is the correct answer. When the system loses entropy, the surroundings increase compensates, and total entropy generation cannot be negative. C. Entropy generation can be negative if the surroundings absorb more heat than the system loses. This is incorrect because entropy generation cannot be negative. It is always positive or 0, never negative. D. The system's entropy always increases as it absorbs heat, and total entropy generation is 0. This is incorrect because while the system's entropy increases when it absorbs heat, total entropy generation can never be 0 unless the process is reversible, and that's not guaranteed. Entropy of pure substances. Pure substances can exist in the compressed liquid, saturated mixture, or superheated vapor regions. The entropy value in the saturated mixture region is determined by the quality and the saturated entropy values. For these conditions, thermodynamic property tables are used as the main reference. Entropy is treated like other state properties such as enthalpy and internal energy. Therefore, the determination of entropy depends on the state condition of the substance. TS diagram for water. The TS diagram shows the relationship between temperature and entropy for water. The critical point marks the end of the saturation curve that separates the liquid and vapor regions. The saturated liquid and saturated vapor lines bound the two-phase region. Outside this region are the compressed liquid and superheated vapor regions. This diagram is very useful for visualizing thermodynamic processes. Isentropic process characteristics. An isentropic process is a process with constant entropy. This process is adiabatic and internally reversible. Since there is no entropy generation, the energy quality is preserved. This process is an ideal model for turbines, compressors, and nozzles. In practice, real processes always approach but never truly achieve isentropic behavior. TS diagram insights. For internally reversible processes, the area under the curve on a TS diagram represents the heat transfer. The amount of heat depends on the process path, not only on the initial and final states. Mathematically, the heat is expressed as the integral of TdS. This gives a geometric meaning to the TS diagram. Therefore, this diagram is very useful in thermodynamic cycle analysis. Check your understanding. Number 3. This question emphasizes the mathematical interpretation of the area under the curve in a TS diagram. The goal is to ensure understanding that the integral of TdS is directly related to heat transfer. This is not just a symbolic relationship, but has a clear physical meaning. This concept is often used in power and refrigeration cycle analysis. Mastering this idea is essential for advanced analysis. Isentropic process in TS diagram. On a TS diagram, an isentropic process is represented by a vertical line. This occurs because the entropy value remains constant throughout the process. Since the process is adiabatic and reversible, there is no heat transfer. The initial and final points have the same entropy value. This representation makes it easy to visualize ideal processes in turbines and compressors. HS diagram insights. The HS diagram is often used to analyze steady flow devices such as turbines and compressors. The vertical change represents the specific work change. The horizontal change indicates irreversibilities or entropy generation. For adiabatic processes, this diagram is very informative in evaluating actual and ideal performance. Therefore, this diagram is very popular in power generation and refrigeration engineering. Entropy and phase changes. Entropy increases when a substance changes from solid to liquid because the level of molecular disorder increases. When the liquid evaporates into gas, the entropy increases even further. The gas phase has the highest entropy because the molecules are the most widely dispersed. These phase changes show the relationship between entropy and the microscopic structure of matter. Physically, entropy reflects the degree of molecular freedom. Boltzmann's legacy. Boltzmann's famous formula links entropy to the number of microscopic states of a system. This relationship shows that entropy is not only a macroscopic concept, but also has a statistical foundation. Boltzmann's tomb even bears this equation as recognition of his contribution. This approach paved the way for the development of modern statistical mechanics. Thus, entropy can be understood from a molecular point of view. Third law of thermodynamics. The third law states that the entropy of a pure crystalline substance at absolute zero temperature is zero. Under this condition, the molecular structure is in a state of perfect order. This statement provides an absolute reference point for entropy measurements. This concept is very important in absolute entropy calculations. In practice, this law forms the basis of entropy tables. Answer: C. A pure crystalline substance at absolute zero has zero entropy, and its molecular structure is perfectly ordered. Explanation: A. At absolute zero, a pure crystalline substance has maximum entropy. This is incorrect because according to the third law of thermodynamics, entropy is zero at absolute zero for a pure crystalline substance with perfect order. B. At absolute zero, the molecular structure is perfectly disordered. This is incorrect because at absolute zero, the molecular structure is perfectly ordered, not disordered. C. A pure crystalline substance at absolute zero has zero entropy, and its molecular structure is perfectly ordered. This is the correct answer as it aligns with the third law of thermodynamics, which states that entropy is zero for a perfectly ordered crystalline substance at absolute zero. D. Entropy is undefined at absolute zero for any substance. This is incorrect because entropy is not undefined, it is explicitly zero for a pure crystalline substance at absolute zero. Disorganized energy effects. Disorganized energy is ineffective for producing useful work. Even if the amount of energy is large, without proper organization, it is difficult to utilize. This analogy explains why energy quality is just as important as energy quantity. Entropy is used as a measure of this level of disorder. The higher the entropy, the lower the ability of energy to perform work. Energy in frictionless processes. If a weight is lifted without friction, no entropy is generated. The energy remains fully usable and is not degraded. Such a process is ideal and reversible. In reality, frictionless conditions are almost never achieved. However, this example is important as a reference for an ideal process. Paddle wheel work effects. When a paddle wheel stirs a gas in a container, mechanical work is converted into internal energy. This process increases molecular disorder and raises the entropy of the gas. Energy is still conserved, but its quality is degraded. Part of the energy becomes less useful for producing work. This is a classic example of energy degradation due to irreversibility. Entropy in heat transfer. When heat flows from a hot body to a cold body, the entropy of the hot body decreases. However, the entropy of the cold body increases by a larger amount. As a result, the total entropy of the combined system increases. This shows that the natural direction of heat transfer always increases total entropy. This principle is consistent with the second law of thermodynamics. Check your understanding, number 5. This question highlights the direction of entropy change of a hot body during heat transfer. The goal is to ensure understanding that the entropy of the hot body decreases when it loses heat. This is a direct consequence of the definition of entropy change. Even though one part of the system experiences a decrease in entropy, the total system still increases. This concept is important for combined system analysis. Workplace friction and entropy. The workplace analogy is used to illustrate the effect of friction and disorder on performance. The greater the friction, the more energy is wasted and the higher the entropy. A well-organized system has lower entropy and works more efficiently. Although this is only an analogy, the physical concept remains the same. Entropy is always related to the loss of useful work potential. TDS relation applications. The TDS relations link entropy changes to changes in energy, pressure, and volume. These relations are valid for both reversible and irreversible processes. They can also be applied to closed systems and control volumes. With these relations, property changes can be analyzed in a more systematic way. This is an important tool in advanced thermodynamic analysis. Properties of liquid methane. The thermodynamic properties of liquid methane show different dependencies on temperature and pressure. The change in density with pressure is relatively small at constant temperature. Enthalpy and entropy are more sensitive to temperature changes than to pressure changes. The specific heat values also vary with temperature, so the constant assumption must be used carefully. This example shows how property data are used in real analyses. LNG turbine insights. An LNG turbine works like an LNG pump operating in reverse. The flow energy of the fluid is converted into useful mechanical energy. This equipment is designed to operate at extremely low cryogenic temperatures. Its main application is energy recovery in LNG processing and distribution. This example shows a direct application of entropy and isentropic efficiency concepts. Answer: B. The LNG turbine operates as a reversed LNG pump, converting flow energy into mechanical energy. Explanation: A. The LNG turbine operates as a reversed LNG pump, converting mechanical energy into flow energy. This is incorrect because the LNG turbine operates as a reversed pump, converting flow energy into mechanical energy, not the other way around. B. The LNG turbine operates as a reversed LNG pump, converting flow energy into mechanical energy. This is the correct answer. An LNG turbine functions by converting the flow energy of liquefied natural gas into mechanical energy, typically for energy recovery in LNG processing. C. The LNG turbine is designed for high-temperature applications in natural gas systems. This is incorrect because LNG turbines are specifically designed for cryogenic conditions and extremely low temperatures, not high temperatures. D. The LNG turbine is used solely for transporting LNG without recovering any energy. This is incorrect because the turbine is used for energy recovery in LNG systems, not just for transportation.
Thermodynamic relations. The ideal gas law relates pressure, specific volume, and temperature. The change in internal energy is expressed as mCv dt. The change in enthalpy is expressed as mCp dt. These relations greatly simplify ideal gas analysis. Under these assumptions, property changes depend only on temperature changes.
Constant specific heat assumption. In many engineering analyses, the specific heat is assumed constant at an average value. This assumption greatly simplifies energy and entropy calculations. Physically, the specific heat actually varies with temperature. However, for a moderate temperature range, the resulting error is relatively small. Therefore, this assumption is very commonly used in practice. Ideal gas entropy dependence. The ideal gas entropy function table contains only the temperature-dependent part. The effect of pressure is included separately in the entropy change equation. This confirms that the entropy of an ideal gas depends on both temperature and pressure. This approach simplifies the use of tables in calculations. In this way, entropy changes can be computed systematically.
Check your understanding. Number 7. This question reinforces that the entropy of an ideal gas depends on two main variables. The goal is to ensure there is no misconception that entropy is only a function of temperature. Pressure also plays an important role in determining the entropy value. This is very important in compression and expansion process analysis. Mastery of this concept is crucial for advanced calculations.
Entropy change for ideal gases. The entropy change of an ideal gas can be calculated using either exact formulations or the average specific heat approach. For small temperature differences, both methods give nearly identical results. The entropy change depends on the temperature and pressure ratios. This makes the calculation relatively simple and practical. This approach is very commonly used in heat engine analysis.
Isentropic relations for ideal gases. These isentropic relations apply only to ideal gases undergoing isentropic processes. It is assumed that the specific heats remain constant during the process. These equations relate the temperature, pressure, and volume ratios. With these relations, the final state can be determined without using property tables. This is very useful in the analysis of nozzles, diffusers, compressors, and turbines.
Isentropic process calculation. To determine the final state in an isentropic process, the initial pressure, initial temperature, and final pressure are required. The entropy value at the initial state is read from the property table based on the initial temperature. Since the process is isentropic, the entropy at the final state must be the same as the initial value. Using the final pressure and the same entropy value, the final temperature can be found from the table. This procedure shows how property tables are practically used in engineering calculations. Answer: C. Specific heat values remain constant during the process. Explanation: A. Specific heat values are allowed to vary during the process. This is incorrect because in an isotropic process, specific heat values are assumed to remain constant, not vary. B. The process is applicable only to ideal gases undergoing non-adiabatic processes. This is incorrect because the isotropic process is specifically used for adiabatic processes, not non-adiabatic ones. C. Specific heat values remain constant during the process. This is the correct answer
as isotropic processes for ideal gases assume constant specific heats. D. The temperature, pressure, and volume ratios are not related in isotropic conditions. This is incorrect because in isotropic conditions, there is a specific relationship between temperature, pressure, and volume ratios.
References. This section lists the main source of figures and materials used in this chapter. The book by Çengel, Bowles, and Kanoglu is one of the standard references in engineering thermodynamics. This reference ensures that the concepts, diagrams, and examples used have a strong scientific foundation. Using a standard reference also ensures consistency with international literature. This is important to maintain the quality and credibility of the lecture material.